A trained deep neural network represents a black box mapping between the input and the output. This can be represented as y equal f of x. So a deep learning model produces an output for every input fed into it. The goal of training is to make sure that this f of x represents the posterior distribution of the labels conditioned on the inputs. So what this means is that given an input, you have to be able to classify that input into the right label or class. So when we train a deep neural network, we usually try to use gradient descent or some form of gradient descent to minimize a loss function that's represented as a mapping between true labels and the labels being predicted by the model during training. So the goal of training is to minimize this value given a set of data points xi and yi in the training data set. So the goal of training is to use this loss function and the training data set to update the parameters inside the deep neural network. So after training is done, we have a good estimation of the posterior distribution of labels or classes given a specific test case. We use gradient descent to use loss function and training data set to update these parameters and as a result have a good estimation. The usual rule that we design using gradient descent is that for all weights inside the deep neural network, over each iteration of training, we update the parameters given this rule where the value of the weight is updated by a constant named learning rate times the partial derivative of the loss function with respect to the weights. The same happens for the biases inside the network, where we take the partial derivative of the loss function with respect to the biases inside the network. This, after training, defines the boundaries between different classes. For a binary case, if we have class A and class B, and this is the embedding space between the embedding space representing the classes that we are classifying, then the loss function and the update rule and gradient descent and the training data set during training lead to this boundary between two classes, where this line defines the border between samples that come from class B and samples that come from class A. The goal of adversary is to find these data points that are closer to the boundary or the border between two classes and move them across this border. So now the network is making incorrect decisions on samples coming from class B. This is usually done by estimating this update rule and this loss function. And then instead of following this rule to update weights and biases, using the sign or the magnitude of the loss function for a given data point and maximizing this loss function instead of minimizing it. This usually leads to a small amount of engineered noise that the adversary can add to the inputs x, so that when this x is fed into the deep neural network, the output is an output that belongs to a different class than the class that x is coming from. This amount of noise is usually limited to a specific p-norm, which represents the amount of deviations that can be added to the input. And the goal of the adversary is that after this noise is added to the input, the amount of noise is so limited that this adversarial example is very close in qualities and features to the original example. In other words, the adversary adds small amount of noise to make changes in the input that are very small, but those changes lead to larger changes in the output. So in other words, the difference between the original example and the adversarial example is limited to epsilon, which is a very small amount, but the difference between the adversarial decision made by the deep neural network and the original label belonging to the original data instance is very large. So in other words, bounded noise added to the input result in unbounded results that are far away from the healthy prediction that DNA should make. We have designed a robust way of training that follows the same way of training using gradient descent and updating the weights and biases in the same manner. We have added one extra step to the process so that we make sure that the values of weights and biases change during training in a way that once the training is done, if a limited amount of noise is added to the input, the amount of deviations that happen on the output of the DNA are also limited. In other words, we bounded these changes between the adversarial output and the original output by the changes applied to the input. So the changes between the adversarial example and the original example. The idea here is that we train our deep neural networks so that the outputs and the changes in the output are bounded by the changes in the input. This means that the adversary, in order to affect the decisions made by the deep neural network, needs to add a large amount of noise. So to increase this bound so that the difference between the adversarial output and the original output is large enough so the data instances coming from class V now cross this border and are misclassified. In this case, then the amount of noise added by the adversary should be so large that it should be very easy for us to detect the adversarial. And the other option that the adversary has is to just introduce a small amount of noise to the input to produce adversarial examples. Since we bound the changes in the output by the changes in the input, the adversary has two options. They either can introduce small amount of noise, in which case the output changes are not large enough for the instances to be misclassified. So the other option for the adversary is to add a large amount of noise to the original input. This large amount of noise should be easy to detect. So the only option left for the adversary to affect the prediction of the DNA is something that's easy to detect.